Okay, guys, so this lecture I'm going to be talking about magnetism. So we started talking about this a little bit in the last lecture. And what we said just is basically there is this magnetic force that is in a force that's an addition and different than the electric force. So if I was going to write the electric force, it would be Q times the electric field. So we're saying that there is another force, so this is the electrostatic force. Electrostatic force. Another force that is we see when there is a moving charge. And so if I was just going to say that also has a Q component that has to do with whatever's being whatever the force is happening on, as the case may be here, times velocity cross this magnetic field. So this is the magnetic field, and this is the velocity of whatever's moving, okay, of the charge. So this is the magnetostatic force. Okay. So and so we mentioned this, and so this, as we can see, as I'm going to mention this quite a few times during the lecture, is that the magnetic force is again different than the electric force. Because, as you can see, the electric force, everything could be sitting completely stationary. The charges that create the force, the things that the force is acting on, they're all could be stationary. There's a vector associated with the electric field, but then say the charge itself or whatever generating the electric field is just a unit charge or a charge sitting somewhere. It doesn't have a vector, it doesn't have a direction associated with it. But in the case of the magnetic force, things are get quite a bit more complicated, although in lots of ways it's similar, as we'll see, to the electric field. But the complication comes from this cross product and the fact that to get this magnetic force, the particles themselves have a velocity which has a direction. So you're not only talking about the direction, the vector of the B field itself, but you also have to worry about the vector of the whatever direction the charge is moving. Okay, so that makes things quite a bit more complicated. All right, so I think I had a few examples. One was the problem of let me just jump to a new example. So let's say another thing which so let's say do an example here. Is a case, so now again, things are getting complicated. We have to keep track of the direction of the magnetic field and the direction of the velocity. Okay, so as we mentioned last time, since we're kind of running out of dimensions here, so we got to, there's the x and the y here, but we also have to keep track of like a third dimension for magnetism because of this crossbar, so it's hard to draw. So by convention, we're going to have vectors going into and out of the screen. Okay, so we have the plane of the screen to draw stuff on. Then I have to draw stuff coming out of the screen and into the screen. And for that, anything that's coming out, anything that's going into the screen looks like a plus. So this is going into screen. or the whiteboard or whatever, a piece of paper, whatever you guys want to think about it. And something like this is anything coming out of screen towards your face. Okay, so that's the convention. So let's say you have a magnetic field. So let's say we have an area where there's a magnetic field, sort of distributed magnetic field. Because I'm drawing a bunch of dots, let me just make the dots here. It's going to be sitting here drawing dots all day. They're coming out of the screen here. Okay, so there's the magnetic field direction is coming out of the screen. So I have a B vector coming out of the screen. And let's say I have a particle moving with a certain velocity straight up. So the velocity of the particle is going like this, and the magnetic field is coming out of the screen towards me. So I would basically try to figure out the force on this thing, on this particle. So the force is QV cross B. So I have to figure out this cross B. And as you guys, hopefully you guys remember the right hand rule. So, unfortunately you can't see a video of me, or maybe fortunately, but I'm going to do a right hand rule sort of analysis. I got, one finger pointed in the direction of the velocity going up, and another finger sort of facing towards my face. So that's this B field coming towards my face. And that tells me that the force is going to be acting like this on the particle. Okay. And because everything is at right angles, the V cross B is at a right angle here, I'm going to get that force is going to be QV times B. Okay. Now, it turns out in a situation like this is a lot like a gravitational rotation type of thing, is that because the force is always perpendicular to the direction of the velocity, then the particle never speeds up or slows down. The only acceleration, remember, is a change in velocity. The only acceleration is in the change in direction. So what happens is this guy will keep getting nudged over, and at each point it'll feel a force perpendicular to its direction of motions, and means it'll go in a circle. Okay, because at each point along here, the force will keep being in a direction that's going to keep it. Again, it's kind of like planets going around the sun or anything like that. And so you have a situation where you have mv squared over r, where r is the radius of your rotation, is equal to qvb, which is the force that's keeping it in rotation. Okay, so in this case, this is kind of like an electron, or not electron, let's call it a particle trap. Okay, so we can basically launch a particle into this magnetic field and get it just to stay there, and it'll just keep rotating endlessly, this particle. And it's going to rotate at a radius and velocity that's going to be something that we can modulate. Okay, so this ratio of this ratio between the velocity. So the velocity is going to be kind of a constant. Okay, so basically this ratio is going to end up being, let's see, the velocities cancel out. Where am I? Sorry. So there's this velocity here, goes out with this velocity. So if I just move things around, V over R is Q over MB. Okay, so this ratio of velocity to this radius, the B field is the magnitude is what I control, right? So I can adjust that up and down. So for the same B field, this ratio of velocity and radius is only going to depend on the charge divided by the mass of the particle. So, one way to look at this is depending on this ratio of a given particle, it would be rotating at a particular velocity and radius that's different than some other ratio. Okay. So in addition to that, let me just talk about something called angular speed that you guys are all familiar with. And that's just given by, so the way you think about angular speed is you think if something has a velocity in a circle, okay, so something is moving in a circle of radius r, the distance it's going to go is 2 pi r, and let's say it'll rotate around that 2 pi r in t period in period t. Okay, so that period t is going to be 2 pi r over the velocity of that thing going around in the circle. So v over r, that ratio is going to look like 2 pi over the period t, and or 2 pi times the frequency, because frequency is 1 over the period. Okay, and this thing is called w, or the angular speed. And the idea is that imagine two things with the same angular speed, they could be moving in two different radius around the same circle, right? The thing on the outside would have actually a lot higher speed because it would need to go cover that distance. It's got a longer distance to go, so it needs to move faster in terms of pure velocity. But in terms of the angular speed, it would have the same angular speed as the one on the inside if they're both going around the circle at the same time. Okay, so basically what happens is this angular velocity is equal to this ratio of charge per mass. So you can basically use this. This is kind of a cyclometer that they use to study sort of charged particles. Okay. I'm figuring out their mass and their velocity, etc. Okay, so this is an example of magnetism. And again, you can see several things here as we had to do like a cross product. We had to keep track of multiple directions, including the velocity of the particle, which we didn't have to do in electrostatics. Okay, so now let's look at what's the force on a wire in a magnetic field. So force on a wire. Okay, so remember that previously in the electrostatic case, we only worried about force on a single charge. Oops. But for magnetism, if a charge isn't moving, there's not going to be any magnetic force on it. So to generate a magnetic field or to feel a magnetic force, charges have to be in movement. So we kind of have to start thinking in terms of wires or things that are moving. But let's take a wire, right? So again, think of a wire that's hanging out in space. And we think of a really small section of that wire. So something with like that with a length dl, okay, and a surface area A. And let's say this is in a magnetic field B. Okay, so remember the force is Q, the magnetic force is QV cross B. All right, so first thing we got to do is figure out what the Q is. Well, Q is going to be this volume of what's in this volume of charge that's going through in this kind of unit of time given by this velocity. So that's going to end up being the surface area times the length dl times the number of carriers n times the charge per carrier E. Okay, so that's going to be the charge. So you can write F or dF, which is just a force on this particular length of wire, to be A N E D L V cross B. Okay, so now um, one nice thing about a wire is, so because the wire directs the flow of your charges, the velocity of the charges, the velocity vector, is going to lie in the same direction as the length vector. So by definition, if that thing goes around, dl goes around, so does the velocity vector. So we can actually keep the velocity, bring out the velocity, and just keep track of the dl as a vector. So this could, you could also write this as a n e v dl as a vector, which is the same direction as v, time cross b. Now this thing is the same as current, so this is going to be I times dl cross b. Okay, now you got to be even more careful. This is a vector, this is a vector, and this is a cross product. Okay, so basically that's the force on a wire having a certain current in space. So for example, if you had, again, if you had a magnetic force coming out of the screen, that's what I'm drawing here with these dots, coming towards your face, and let's say you had a horizontal wire here where the current was going in this direction. I have to draw the current carefully because of the right-hand rule. You could basically end up feeling a force that's pushing you up. So you could sort of physically keep the wire up. Okay, so this would be the force. And in fact, BLI, so let's say this was the length of your wire. If that equals to the mass times gravity of the wire, you could sort of, levitate sort of the wire in a magnetic field. Because, B is coming out of the screen, The current is going in that direction, so that's where the DL is pointing to. So with the right-hand rule, the force would be pushing up against the force of gravity. Okay, that's another example. All right. What else do I want to say? Okay. All right. So, okay, so now let's look at another example, more complicated. Okay, let's say you have I'm going to try to draw a semicircle. It's good enough for me there. And let's say the wire is doing that, and there is a current running through this wire. And let's say it's in a magnetic field that's pointing up. And assume that this is, uniform. Oops. Yeah. And sort of it's in the plane of the screen, obviously. Now, let's say I'm only concerned about the force on this section. Okay. Now, obviously, there's going to be a force on this section and this section, and I can't get rid of those sections because I need to find some way to get my current here, right? So the current needs to come from somewhere and go to somewhere. If there's no current, there's no force, there's no magnetic force. So I would have to, but for this problem, I'm only concerned about the force on this semicircle. Okay, so let's first think about which direction the force is going to be going to. So the way I drew this, let's see. Okay, so my dl, so remember the force is I dl cross B. So the dl is kind of, oops, that was a bad color choice. Let's try this one. The dl is running in this direction. Okay, each one of these guys will be a different dl moving around. Okay, and so I got to figure out this. I is I, that's the current. Then I need to figure out that I dl be sine theta. Whoops, what the heck? Sine theta. So that's what that force would look like. So this is a small bit of force on this section dl. So I'm going to calculate that, and then I'm going to integrate that force across the half circle. Okay, so let's think about this. So make sure I'm looking at my good notes here. Okay, good. All right, so let's think about this thing over here. Okay, this dl. There is a theta here, angle. Let's see. Draw here. So from here to here, there's this angle theta. So, we're going to be trying to integrate this angle theta from 0 to pi. As you guys can see the thing, this coming. So there's this angle theta here, but the theta I want is sort of that, right? I want to know what is this, the B field is pointing in this direction, straight up, okay, and DL is pointing in this direction, which is tangential to the line here. Okay, so I want that theta. Now I'm going to claim that that theta, that this, and let's call this theta prime, and I'm going to make the claim that theta prime is equal to theta. And what lets me do that? Well, there is a old kind of theorem that says if two lines have angle theta, so between them, then two lines that are perpendicular to these two lines will also have the same angle theta. So these are the two lines, and notice, okay, one line is the B field here is perpendicular to this, because we made it so. We said B is going straight up. And then the second line goes from this radial line. Well, the tangential line on the semicircle is going to be perpendicular to this. So if this angle is theta, so will this angle. So I'm going to say that this is the case. Okay, so I'm going to have, by the way, this is coming out of, let's say, the screen. So I want to call it K, I guess, or coming out of screen. That's the direction. Again, by the right-hand rule, you got to put, again, one finger going towards the, if you guys don't remember the right-hand rule, it's kind of a good time to remember it. I'm still sort of dusting off mine, but it's going to be coming out of screen. I just called it the K vector, I guess. Okay, so basically this sine theta prime I'm saying is the same as sine of theta. So it's equal to I dl b sine of theta. So df is going to be equal to this. Okay, and then to find out the total force, I end up integrating df. So the total force, the value of the force is going to be the integral of this guy from 0 to pi I b sine theta dl. All right. So now I got to figure out, I got this dl, which I probably want to put in terms of d theta to be able to integrate. So this is how I think about it. This is how I thought about it. Is if you go all the way around the circle, so 2 pi r is going to be that in the case of that the full radius is going to be 2 pi, right? Radius 1. And so I'm trying to think of this. So basically, I'm trying to figure out what is this dl, okay? That dl is kind of a wedge, okay? Or you want to think about basically like that, or you want to think about it like that, is like a wedge that is d theta. You can divide that into a bunch of d thetas, okay, angularly. So if 2 pi r distance is, 2 pi, then this little wedge, this dl, is 2 pi. Sort of this ratio is what I'm like thinking is going to be what you get. Okay, so we can get rid of the 2 pi's. I don't know if I explained that really well, but dl is r d theta. Basically, the idea is that you're trying to replace this thing by like an idea of how many of these wedges would you get. You have to multiply it by r times that angular wedge. Okay, and so I get, let's see, 0 to pi IB sine theta r d theta. So I'm going to pull out IBR, and I'm going to end up with 0 to pi sine theta d theta. And that's just going to be, this is just minus cos, this integral is going to be minus cos of theta. And so I end up with 2IRB. Okay, so this is the force amplitude, and the actual force vector is going to be this times k, or coming out of screen. And I'm not going to show this to you guys, but I'm just going to tell you this, that in general, because I'll be using this shortcut later. This might be in your homeworks, maybe not. Not sure. But in general, if a wire of length L is perpendicular to a B field, to a magnetic field, the force on it will be, the amplitude of the force will be BLI. So I want to kind of remember that, because we'll be using it in a minute as a shortcut. And it turns out that basically if the wire, so for example, in this case, the wire is not fully perpendicular to the B field, we basically figure out the component that is perpendicular to the B field. So if we have this thing, okay, I think about this would be the same as this part of the wire, this length, this component, this shadow wire running perpendicular to the B field is actually R plus R, so that'd be 2R. So this 2R would be the length B times I. In fact, it'd be the case even if you had like a really funky wire, it would be the same. It'd be the length of the equivalent length of the wire running parallel to the B field would sort of be the one that you would use as the L here for calculating this force. But just remember this sort of shorthand. So that's the story. So you would end up with this current. You would end up feeling this in this magnetic field with this current. You would feel a force coming out of the screen. Okay, so again, illustrating that we need a current to flow to feel this force. Looks like you need to have a current flow, and you need the direction of the movement to be, if the direction of the movement was, parallel to the magnetic field, you'd feel no force. So you basically are thinking about the components perpendicular to the components of the movement perpendicular to the magnetic field that would feel that force. So again, it feels like quite a bit more complicated than electric field. Okay, but that's just how it is. That's the nature of magnetism. All right, so what? So now this wire, length of wire, is gonna feel a force coming out of the screen. Let's do another example, and this example is sort of walking us close to a very useful object. So stepping us closer to it. So the idea behind this example is that we would somehow have a current loop. Okay, I'm going to do this. I'm going to draw this really badly, but hopefully I'll clarify it in a second. Imagine this loop is how should I draw this? That it's boy. Let me draw it like this. So this thing is not helping. So let's just say this loop is like this. So what am I trying to draw here? So it has a current going around the loop like this. Okay. So, and then there's a B field pointed in this direction. So current's going in that direction. Okay, so what am I trying to draw? If I look at this from the side, okay, I want to draw basically, I'm going to be looking at it on this edge. So if this is, let's say if this is W, this edge is W wide, and this is L, okay, this would be W. So on edge, and then the B field would be pointed up that way, like here. So I'm trying to draw this as like sort of a really bad three-dimensional drawing showing that there's this thing is really, if I just think about the screen as being two-dimensional, it's coming out of the screen, this width, and L would be that way. Okay. So let's see, what else do I want to say about this? So the current's moving around. So in any one of these places, excuse me, you want to think about, so these will be like little DLs. Okay, in each one of these places, you want to figure out, there's a force on this loop of wire, any one of these places, because it's got a current, we got a magnetic field, so there's a force here. So we got to figure out, where's the force that's perpendicular both to this DL in each one of these segments and to the magnetic field. So the force ends up being in different directions. So it's in the bottom here, the force is kind of going that way. The top, the force is going that way. Here, the force is going this way, and here, the force is going that way. Okay, so now this force and this force are going in sort of opposite directions. So they're going to cancel each other out. Okay, now this force and this force, if I draw them here, are going to look like this. This is this F. And there's another F here. Okay, and then there's, the magnetic field is here. So this is, again, this is looking at this edge on. So that's what it would look like. And this should look pretty familiar to us. It's basically kind of looks like a dipole, right? If you guys remember, whoops, don't do that. I'm going to redraw it here so I can put some angles on it. But so remember, like we drew a dipole having two charges in a electric field that was running in this direction. So this was a electric dipole. And as you guys you will see very soon, maybe you already see, is this is kind of going to look like a magnetic version of that dipole, with lots of stuff being analogous to the field. But to begin with, you can kind of see the analogies with the electric field. In a magnetic dipole, we have, let's see, depending on which W I'm drawing, but you have current flowing. So you have I. So the current has to flow. In an electric dipole, we actually had charges on two ends of some kind of a stick. So there were actual, if you went to the ends of the dipole, you'd actually see individual charges that are just sitting there. Whereas in a magnetic dipole, we have a current going around the loop because there's no such thing as a magnetic unit charge. Like magnetic fields or magnetic things that sense magnetic stuff are always sort of moving charges. Okay, so that's one. Second thing was the E field was going in this direction, whereas the B field's going in this direction in this case. Okay, so now let's look at the force. Sorry, so now if you have a B field going this way, you have a current, depending on if I'm going to be looking at, let's see, if I'm going to be looking at sort of this side or this side, depends on which is the current going into the screen in this case, or coming out of the screen over here. But let's kind of think about the torque. Basically, you're going to end up having a torque on this loop. So this loop is going to start, this force is going that way, that force is going that way. So if this loop was being held, it would start rotating. Okay, so the force would be here, force would be here. So this thing would be experiencing sort of like a torque that would try to flatten it out. Okay, and let's try to figure out what that is. So now the torque you could kind of calculate around different sort of rotational points, if you want to think about it that way. But let's sort of think about calculating it here. You could do it here, you could do it here, you could do it here. You just have to kind of make sure you sum up all the factors. Okay, but let's think about doing it here. Okay, so let's see. So to do that, first let's define some angles. So let's call this theta. And let's call this the area vector. Okay, so again, B field is pointing this way. Straight up. So this theta, but again, we want this theta prime. So I'm going to again make the claim that theta is equal to theta prime. And why is that? Again, I'm going to say that two things that are perpendicular are going to have the same angle between them. So one is this theta. Oops. So this theta is basically looking at the separation between this and this. Okay. And so that is the B field is perpendicular to this guy. And the area vector is perpendicular to this guy. So I'm going to say that theta prime is equal to theta. So I'm going to say that the torque that you would experience here would be BL, sorry, maybe I'm going to write it a different way, BI LW, that's the area, sine of theta. Because, okay, so that's going to be sort of the torque on this thing. Okay, so let's see, whoops. Am I charging? Yes, okay, good. Sorry, guys. Okay. And remember that sort of also equation for torque is tau, and it's something cross the B, okay? So in this case, mu is, if you want to compare this equation and this equation, the mu is going to be the area, because this is the area, times I. Okay, so this guy is going to be this mu. Okay, but L times W is equal to the area. And so this is kind of the analogy between the magnetic dipole and the electric dipole. The magnetic dipole will feel a torque that is dependent on the magnetic field, and then dependent on this area times area of the loop times the current flowing through the loop. Okay, and the field in this situation is going to try to set the torque equal to 0. Okay, it's going to try to rotate this guy till it sort of flattens it out. But that will only happen if you to get to 0 torque. It only would happen if the area, so this area, so I'm going to redraw it here, thou is equal to A I cross B. So if, remember the area we're defining as, if I was going to draw the area vector, it would be coming out of the center of this coil, this loop. Okay, so that area. So it's going to rotate this guy till that area is parallel to B. So either that case, so B is going to try to force the torque to be 0, and that happens in two cases. One of them is that A is parallel to B. Notice the area, which is coming straight out of the center of the loop, is parallel to B, the magnetic field. So meaning this is going to rotate till this loop is kind of sitting like that, facing that way. So here it'd be kind of like that till this guy is facing up towards the magnetic field. So it's either in this case, or so it's either they're parallel, or I don't know how to write anti-parallel. So I better not even write it. So, and that's the case when this loop is flipped the other way. Okay, so that A is pointing exactly opposite to B. Okay, so those are the two options. If you remember, in the case of the electric dipole, you could either get the situation where this guy was lined up like this with plus Q, minus Q, or you could have the case where you had minus Q, plus Q. Those are the two options. Okay, so you have sort of similar two options in a magnetic field and a loop about the points of equilibrium. Okay, and now, and the points of equilibrium, these points are, so there's equilibrium points, which are where A and B are, A being the area vector and being the magnetic field, or 0 equilibrium points are points of max or min energy. Those are the two cases, just like the dipole was. Okay, um, so you can show that in this case the potential energy is minus mu b cos theta, which I'm not going to show here, or minus mu dot b. And if I was going to draw it, this, I don't know if you guys remember, but we drew the same kind of thing in terms of theta, energy for electric dipole, and you kind of end up in a situation where you have, because you have this cos theta, you have a situation where it'll do stuff like that. Because of this negative sign, here you would get cos theta would be minus 1 at pi. So this would be when they are parallel, I guess. The A and the B are parallel. With this mu and B. So mu is pointing in the same direction as A. And I guess this would be the anti-parallel case. Okay, and so so this would be the point of minimum energy. And this would be the case of maximum potential energy. And so this is when, again, thinking of this current loop as your magnetic dipole, the minimum energy would be when this guy rotates to be in the same direction as the B field. That'd be the minimum energy. And then the maximum energy would be the case where this guy is pointing down and the B pointing up. So they're both stable cases, but you can also, just like the electric dipole, is one of them is really stable. It's like sort of a pebble or a marble sitting at the bottom of the hill. If it gets a little bit of disturbance, it's going to just kind of come back to this minimum energy case. The other stable point is if the loop is rotated around, it's going to be, if it gets a small disturbance, it's going to change its energy quite a bit. So again, if this thing, this A, is pointing down towards away from the B, if it gets a little bit of disturbance, it's going to change its energy quite a bit. Go from max to min very quickly. So again, this is called a magnetic dipole. And the difference being that in an electric dipole, okay, so let me just write, so this is magnetic dipole. So magnetic dipole. And so its torque on it is going to have a dipole moment across the E field. So this was a, sorry, no, this is the, this is the electric dipole equation. Okay, and for electric dipole, the dipole moment P was QD, and the energy was minus P dot E. So for a magnetic dipole, tau is, we have is mu cross B. With the dipole moment being defined as, what is it defined as? Area times I. And the energy being defined as minus mu dot B. Okay, so very analogous to magnetic dipole, electric dipole in lots of ways. They sort of act the same way. They try to sort of line up with the field. Their energies look very similar. They either end up with like a lot of energy if they're exactly pointed away from the field, or little energy, or minimum energy when they're pointed, or zero energy when they're, I guess, when they're pointed towards the field. The one big difference, obviously, is that if you actually look at an electric dipole, let's say this is the E field. If you look at the electric dipole, which I'm drawing in the wrong place, sorry. So if you look at an electric dipole, you'll actually see a plus charge and a minus charge at either end of this pole. But in the case of a magnetic dipole, there is no actual magnetic charge because there's no such thing. So what you have is a current loop that is trying to line up with a magnetic field. Okay, but it looks like, we'll have like similar equations to an electric field. It'll have a moment. It'll have energy. Again, a lot of stuff is analogous between a magnetic and electric field, but it's just that there is no such thing as a magnetic charge, or at least one that we've found yet. So to get sort of magnetic things, you need to have these loops of current or moving velocity, etc., and that's sort of the difference. But basically, in either case, you can have a dipole. Okay, guys, so now let's say we have this magnetic dipole. Let's do another example. This time we're going to look at something that's like a very, very useful device that you can use using this magnetic, or build using this magnetic dipole, and that's a electric motor. Okay, so let's see how this is made. So imagine if you had two bar magnets, so two permanent magnets, quote unquote. So I'm going to try my usual bad drawings to draw this for you. So let's say this is one bar magnet, and let's say I have another bar magnet kind of going here. So they're facing each other. Try to move this over. Okay. And so you would have a magnetic field sort of going from one to the other, right? Because you have these bar magnets. So this is the bar magnet, and this is another bar magnet. And let's say I had a wire loop, and I'm going to try to draw this in between, something like that. And let's say these wires come out. So basically I have current running through this, and this is sitting in between like these two bar magnets. Okay, so this is the direction of the current. This is or sort of area vector coming out of the loop, and the B field, the magnetic field, would be kind of running in between these guys. Okay, so as you can imagine, if this is, we said represents a magnetic dipole, and if it's sitting in a B field like this, there's going to be a torque on this dipole, and it's going to force this guy to go in this direction, so that this loop basically the area, so the loop is going to go in this picture. The loop's kind of going to go like this, and the vector B is going to try to line up with the vector B. Okay. So basically, you get a flip or a rotation, which is kind of a good start if you want to have a motor to have basically, this current and this magnetic field leading to a rotation. But there is, and then you need you. So let me just draw one more thing here. So you need some current here. So I'm going to put a battery across. So a battery for current. So okay, so that's good. It's a good start. But if we just build this, it's like has a real limited use because it's just going to rotate once or partially just enough to line up the B field. BA is going to line up with the B field and it's just going to sit there, right? So it's going to like rotate once or semi-rotate once. Okay, so how do you make this into something? The idea is we want to have something that's constantly rotating. We want to kind of create an electric motor from this. So what do we do? Well, one option is you can replace this with a AC sort of signal. So instead of having a direct current, you can have an alternating current. So basically you have your loop running like this, and then say it flips, and then this guy changes the direction of the loop, and the current in the loop is going to go the other way. And then basically, it starts rotating that way because every time the dipole feels like it's lined up, it's happy to be in this low energy state, you completely flip the direction of the current to the other side and you make it rotate again. So you keep up that process and you're going to get this rotating thing. Now, that's okay, but again, sort of an AC current, there is like if you think of the alternating current coming out of the wall plugs, it's at 60 hertz, it's at a particular frequency. And the other thing is that if you're driving around in your Tesla and you want to use this as the motor, if you want to hook up this to your wheels so that it takes you places, the Tesla has batteries, so it doesn't have necessarily alternating current directly coming out of it. It has a DC current coming out of it. So how do you deal with it there? And so this is something called, they have a brushless motor, but this is with a brush. So what you would do in that case is you would sort of replace this thing with this, you'd sort of create these electrodes that are half circles. Connect this to this, that to that guy, okay? And then you would have your battery or DC source connected with a spring to this side, and spring. Call it a spring or a brush. Sometimes you hear about brushless motors, spring or brush. Okay, so what happens is so this guy would also rotate along with your loop. And so as it rotates to a full length, basically you end up rotating the circle. So as soon as it rotates, it's going to basically, this brush at some point is going to start touching this side, and this brush is going to touch this side, you can imagine, and basically flipping the loop. And basically in that way, you can, with a DC voltage source, you can get from this magnetic dipole, you can get a very useful thing, which is an electric motor. And I'm not 100% sure if this is what's running in electric cars, this kind of motor that's connected to your wheels, or I'm sure it's something, even if it is with this principle, it's something probably much more sophisticated. But that's kind of the idea behind, a useful thing that's coming out of this magnetic dipole, one of the many useful things. Okay, guys. Continuing on, the first part of the lecture was about, so the first part was, how do things reacting to magnetic fields? In this second part, we're going to talk about how do, specifically, how do moving charges or currents, how do they create magnetic fields? How do create magnetic fields? Um, so, there's, in the end, everything is, of course, produced by charge, but so a magnetic field, so if you guys remember so far, when we were talking about electric fields, we were talking about static charges. And the reason we did that was because it's a lot easier to deal with static things. We basically said we're going to leave things as they are and then see how they create an electric field. The problem with moving charges is that if things are moving because of uh, because we have to keep track of things. Let me take a step back. So because of relativistic reasons, right? So if something is moving somewhere, think about a moving charge somewhere far from us. Its effect are not going to be immediately apparent at our location. Okay, so it's going to take basically the amount of time it takes light to travel from the location where the charge was moving to our location for the effects of that electric field to be felt here. So this is if we allow for moving charges. So if you're analyzing for moving charges. That means if we allow, or if you're looking at a situation of moving charges, then we have to keep track of historically how the charges were moving because what they were doing, some time ago would be affecting what we see right now where we're sitting. So, for example, there's nothing in the work we did in Coulomb's law that says, the charge that's moving or is moving, say, a light year from us or many thousands of miles from us isn't going to create a magnetic field where we are at, but it's going to certainly take time for that effect to be felt. So got around that problem so far in the case of electric fields because we insisted that we're looking at electrostatic situations so far. So we're saying the charges are fixed. We're only concerning ourselves with fixed charges. So right now they're just kind of sitting there. So they've been where they're at. They have always been where they're at. And so we don't worry about the amount of time that it takes. Basically, it's a situation that's stable. So that's in terms of the electric fields we've looked at so far. So that's why we've been so far. It's been we've kept saying electrostatic analysis, I guess is how you look at it. Okay, now in the case of a magnetic field, we've got a kind of another set of problems because magnetic field is created by moving charges. So from the get-go, this could really make our life even more difficult. As we keep mentioning, we got these cross products and stuff for the magnetic field, but like, it's based even on a moving charge. So are, we can't just use this idea that the charges are fixed. Um, and so it could really complicate our situation. So the way we get around that problem or create an analogous situation, so analogous, try to create analogous situation to electrostatics is to say we're only going to look at constant currents. Okay, so that's a situation where, a current is constantly going around the same loop. So the current is constant, and the loop location itself is constant. So that's analogous in some ways to having a static charge for an electric field. So we're trying to use the same kind of situation, but again, because a magnetic field requires a moving charge, we could start by thinking, or you guys may be tempted to think, what if you had a charge that was moving? This wouldn't work because notice that if you had a single charge that was moving through space, it's not a static situation. It's going to be here, then it's going to move here, then it's going to move here. And we got to keep track of all that movement and velocity and all that stuff in the sense of how it's going to create a magnetic field. Okay, because, in the same way that if you are in a car by yourself on a highway, you can't create traffic by yourself. Say you're driving, 50 miles an hour down the highway. It's just there's a car wherever you're at. But if the highway is full of people with a constant flow of cars going by at 50 miles per hour, that's the traffic. So we say that we have a constant current in a loop that's not going anywhere. That's very different than saying a moving charge. Okay. And in that case, sort of we can get around this situation. Now we can kind of look at it more like an electrostatic situation and just say, oh, we're looking at a constant current and not something that's moving. Okay, so hopefully that makes sense. Now, let's say we had a constant current. So we want to look at what kind of magnetic field it'll generate. So let's put it in a XYZ coordinate space. And then let's say this guy is sitting somewhere out here, this segment of wire. Okay, now we're going to look at a segment of wire. So the length of this, this is a very short length of wire, and its length is dl, and that has basically a directionality of that current along this dl is in a certain direction. That's the direction of the vector. Now, in reality, okay, I don't want you guys to get confused. In reality, you will have, you can't have a current in a segment of wire. This is part of some wire going around, but we're going to look at just this segment of how much magnetic field this segment looks at. So just keep in mind that we're looking at a small segment of a wire carrying a current that's part of a bigger wire segment. Okay, now let's create some definitions. Let's say R is the vector from the origin to this thing. And then let's say we want to look at we want to calculate B field at another point, at this point. And let's say that is R prime is the vector from the origin to where we want to look at. And then, so then by definition, then um, the difference between these two vectors is going to be r minus r prime, two vectors. Okay, so here then the magnetic field, the incremental magnetic field caused by this is mu naught over 4 pi I dl cross E between r and r prime divided by the distance of r minus r prime squared. Okay, so this is called the, I don't know how to pronounce it, the Biot-Savart law. Okay, which basically, basically gives you the value of the magnetic field caused by this incremental length of wire at this location. So this absolute value, okay, that's the separation. Notice that is an absolute value. So let me clarify some of these things. So this is um, so this is the value. Let's see. This is the absolute value, or sort of scalar value of the separation vector between the 2 points. So notice this is the vector, and then we're taking basically the length of it and scoring it. This is the unit vector from R, so from this guy to R prime. Okay, so that's the Biot-Savart law that sort of describes how this magnetic field is created. And we're going to do some examples here of, an entire loop, and then, sort of looking at magnetic fields at different points. Very analogous to what we were doing with, say, Coulomb's law. Okay, but we're doing it for magnetic fields now. So again, I guess I'd like to point out that, beware, this is part of the reason why magnetism, I think, has always been more difficult for me to get a feel for, is you can see this could get has, this kind of cross products. And now we have, if you remember, for the case of electrostatic field, the charge would be, for example, sitting here, there wouldn't be a vector associated with the charge, it would just be a location associated with the charge. And here there is a direction associated with the charge. So, we have these cross products and stuff which can make our lives a little bit more difficult, or a lot more difficult than electrostatics. But anyhow, let's jump in, and I think you guys will see that. All right, so the first example, say we have a loop of, we'll do it this, didn't do it. I'm just going to draw it like that. So say we have a loop, circular loop with current going around it, and then it is, we're looking at sort of the z-axis at its center, and let's say we want to find the field on the z-axis. So find magnetic field here. And let's say the radius of the loop is r. And again, we're doing this because we have a symmetric situation. Because if, for example, let's look at the current right here. right? This is so imagine this loop is, drawn it like this. I've drawn the loop like this, but imagine this loop is sort of cutting through the my your screen essentially. So the current is coming out of the screen here, and then we're going to look at the magnetic field here. Okay, so we basically need to first figure out, so this cross, well, we'll write the whole thing down, but basically you've got a situation where if I want to draw, so the current, again, the current's coming out of the board here, okay, and so let me just write that down. So we're going to look at this incremental length of current coming out of board. Okay, so there'll be a corresponding current here on this other side. That's the current going into the, like, it's not really the board, the screen. Out of the screen, into the screen. Current here is going into the screen. And the reason it's convenient to do it this way again, and we're doing a very special case and on the z-axis, is, as you can imagine, we're going to end up with like a magnetic field pointing here, and then we'll end up with a magnetic field sort of pointing here, and then these x values components, the horizontal components, will cancel each other out, and then we're going to end up with a component just in this direction. Okay, so that's the idea behind doing this symmetric activity. So this is how we're setting up a very symmetric situation. We are setting up symmetric situation to get z pointing in z direction only. Okay, so let's look at this now. So having done this, we're going to end up with the magnetic field caused by just a small segment here. So again, we're going to follow this equation. It's going to be mu naught I over 4 pi. So let me just write the whole thing, dl cross E r prime. Okay, so R will be sort of let me just over R prime minus R minus R prime, the absolute value squared. Okay, so let's take a look at the individual components here. So if you look at the sort of the cross section between this length and the magnetic field on the screen, got to think of what does this cross mean. So remember, this will be dl E r prime sine theta. ER is like a unit vector, so this will just be 1. So it's really dl sine of theta, and this theta being the angle between dl and what we want to figure out, which is the magnetic field. So think of it this way. So the DL, okay, because the DL here is pointing perpendicular to the screen. Okay, so it's coming out of the screen, and here it's going into the screen. So really and then the magnetic field is on the plane of the screen. Okay, so since if you have something coming out of the screen, and then you want to know the angle of that with respect to something on this anywhere on the screen, anywhere really, the angle between those two is always going to be perpendicular. So this is kind of room for getting some confusion here in this cross product. But we're trying to figure out the magnetic field on the screen, okay, and then this guy's coming out of the screen. So the theta is going to be 90 degrees, and sine of theta is equal to 1. Okay, so if I was going to write this as 4 pi, we're going to get dl sine of 90 degrees, or 1. Okay, and then we want to figure out, again, because we said by symmetry, this guy, let me just draw this, define this guy as this distance as z, okay, and this angle, this angle as alpha, as we're using theta for something else, so we use this as alpha as this angle. Okay, so if we want to think about this, we want to get basically the distance from here to there, okay, and sort of the direction. Now we got to figure out also, this is also alpha. Okay, and remember I'm coming up with this by saying that the angle between two lines, this alpha, is the same as the angle between, this angle will be the same if you're looking at the angle between two lines that are perpendicular to these two lines. Okay, so this line is going to be perpendicular to this guy, and the z-axis is going to be perpendicular to this guy. So basically this alpha and this alpha are the same. So I want to figure out this alpha. So now I want to see the component of the magnetic field just in this direction, okay, and this distance. But I want to use this angle because then we can sort of integrate around this circle. So I'm going to make that be over z squared plus r squared. Okay, that's this guy. And then the whole thing, because we want to look at, we were saying that due to symmetry, you're only going to have a component in the z direction. That'll be the cos of alpha. So this is component of B field in z direction. All right, so this is going to be mu naught I. So if you want to integrate, let me just get the value, and we know it's pointed in the z direction. So integral of is mu naught over 4 pi, or z squared plus r squared. This cos of alpha. I think we did this for the electric field, so I'm not going to do it too carefully here. So it's r over in z squared plus r squared to the 1/2. So integral all this times dl. Okay, and that's gonna be u naught. So the only thing I'm integrating is really dl. And if I'm integrating around the loop, the length of that is going to be 2 pi r. So now I'm going to plug in everything. So really I want to basically, let me just clarify that. The only thing I'm integrating is dl. And then this dl is going to be 2 pi r. So I'm going to end up with mu naught I over 4 pi 2 pi r squared over z squared plus r squared to the 3/2. Okay, so that's going to be the magnitude of the electric field, and then it's going to be, pointing in the z direction. I don't know, let's just call it E of z. It's in the unit vector. Okay, so that's going to be at an arbitrary point on the z-axis. If you have a loop with the z-axis at its center, that's what you're going to get with a constant current I flowing through it. Okay, now let's figure out if you look at the magnetic field at the center of the loop, so at loop center, we have z is equal to 0, so B at z equal to 0 is mu naught I over 4 pi 2 pi r squared over r cubed, and so that is going to look like mu naught I over 2r Tesla. Remember, Tesla is the unit for magnetic field, so that's the value of the magnetic field, and it's going to be pointing straight up. Okay, it's going to be pointing up because the current is going in this direction. Okay, it's going to be pointing up, and if the current was going in the other direction, it would be pointing straight down. And one way to remember that is, if you guys can't see my right hand, but if I wrap my right hand kind of in the direction of where the current is flowing, so yeah, you guys won't be able to see it. So my fingers, everything except my thumb, is pointing in this direction because that's where the current's flowing. And so my thumb is that will give you the location of whether it's going up or down. Okay, so in this case, it's going straight up. That's equal to 0. Okay, the other place we want to look at is, let's look at, let's see, at z goes to infinity. What does it look like? At z goes to infinity, b goes to mu naught I pi r squared over 2 pi z cubed. Okay, and this is the area of the loop. Okay, and then remember that the area of the loop times the current through the loop gave us dipole moment. It was defined as a dipole moment of the loop. Okay, so if you think of it that way, okay, so we end up with this sort of magnetic constant times this this dipole moment, in this case of a magnetic magnetic dipole moment of a loop, and then it has this 1 over z cubed component. And this is very similar looking in that case, sort of with that definition, This looks like the E field for an electric dipole. So there's this, there's a lot, as we'll see, there are all these analogies between the, electric field and magnetic field, between an electric dipole and a magnetic dipole. The differences are, if you go look at the electric dipole, there's an actual, there's actually charges at the end of an electric dipole. There's a two equal and opposite charges at the 2 points of the dipole. But if you go look into a magnetic dipole, you won't actually find a magnetic charge at the ends of the dipole, because as far as we know, there are no such things. There's no sort of a magnetic point charge. We're just going to be it's basically a definition around a current loop. But otherwise, the currents look very much the same. The fields, the way the dipole, the fields from a dipole look, etc. It's very much the same, except the dipole moments are obviously different, and these constants. Remember, it was an epsilon naught in the case of a electric field. Okay. Now let's look at the case where we have. Okay, so that was an example. So now let's look at something else. You can basically, excuse me, you can basically stack up. Let me do it this way. Let's say you had I don't know, like a cardboard tube or something, and you wrapped a bunch of wires with current going. But actually, sorry, if you had one wire sort of looping around this, you wrapped it around. So essentially, you have a bunch of, one way to think about it is you have a bunch of loops going around this thing. I guess there could be separate loops too, but let's say you had this kind of situation. Then what you would end up with is oh, one more thing I wanted to say, sorry, about this magnetic dipole. Before we get into this, let me move this over to draw something else here. Oops, didn't. Okay, I guess I'll have to draw it again. Okay, no, let me try it. Let me just be lazy. This probably would be so easy to draw. Copy. Okay. Yeah, it would have been easier just to redraw it. Anyway. So, the other thing about the dipole is that if you were gonna draw the, if you were, let's say we just calculated the magnetic field around, at just R. So we calculated the magnetic field just along the z-axis, because at other points there aren't, the symmetry, you only get the symmetry on the z-axis, right at the z-axis, so you can it's easier to calculate it. So that's why it's, more difficult to calculate the magnetic field anywhere else. But if we were about to calculate it, or if you did, then you would end up with something that looks very similar to these magnetic field lines of a magnetic dipole. So, and then, it looks kind of the same around here. So again, that would look very much like the electric field lines of a dipole, with the exception that with the magnetic dipole, you're looking at a loop with a current going through it, and not, the individual charges. Okay, so just wanted to mention that in terms of the the magnetic fields. So coming to here, if we had a bunch of these loops stacked up, you would still also end up with these magnetic field lines going across. They would all kind of add up together. And not drawing these too carefully. And this looks a lot like a situation of having a bar magnet with a north and south, and same as similar to this currents going around. So I guess sort of, we figured out what's going on with the electric field here, but we really haven't talked about what's causing this magnetic field in the bar magnet. Here we got a current loop, but this bar magnet doesn't look like it has current going through it. It's just sitting there by itself. You haven't applied any current. So what's going on with this magnetic field? Where is it coming from? So, it's interestingly enough, it's coming from a very similar thing. So although there's no current in the bar magnet, but think about a situation where you have a bunch of atoms all sort of stacked up next to each other. So let's say you have individual atoms, okay, and then you have electrons going around these atoms. And let's say they're all kind of stacked up and lined up together. So I'll draw these currents. So these are the nuclei. Nuclei. So if you look at the total current going on here, the interesting thing is that in all the regions on the interior, so let's say here you got a current going this way, and you have equal and opposite current this way. So on all the regions, so this one is going this way, this guy's going this way, and all these regions on the interior, the currents sort of cancel each other out, and the only place that they're left is at the periphery. When you sum things up, you end up with the total current on the periphery. Okay, so if you have a situation where, let's say if you're looking at a bar magnet or some kind of material where all these guys are sitting there stacked and everything's pointing in the same direction, you get the effective aspects of a current going sort of in a loop, very much like this situation. Okay, so that's great, and that's why there are very few things that are magnetic by themselves, because usually what happens, and say if you're looking at a piece of paper or something or a piece of wood that's not magnetic or whatever, it's fairly rare that you get all these atoms sort of lined up together, and the spin of the electrons around the nucleus is in the same direction and so on. And it's only in those kind of materials that you end up having sort of this bar magnet situation. So it's a relatively rare situation So that's why not everything is magnetic. And in fact, if you take a magnet and you heat it up, what you'll end up doing is by sort of causing motion or jiggling or vibration of these atoms, you'll see that the actual magnetic field drops as the temperature goes up because all these atoms that were lined up to cause this magnetic field now start sort of getting misaligned. And so the magnetic field value goes down. And in fact, any magnetic material, you can heat it up to the so-called, I'm probably going to misspell this, Curie temperature. And that's a temperature at which the magnetic field just completely disappears because you basically misaligned all the um, all the uh, or enough of these atoms from each other. All right, guys, so now let's do another example on finding the magnetic field. Again, this is like sort of should remind you the stuff we did on for electrical field. So let's say you have or analogous to it. So let's say you have an infinite wire carrying a current I, and we want to find the magnetic field, say a distance A. Find magnetic field here away from the wire. Okay, so what we do is again we sort of again very much like we did for the electrostatics, we come up with a length of pick a length wire, and we say okay, for that very tiny length, what is the distance, angle, etc. to this point? That'd be the theta. And so in this case, if you notice, the current's going, the DL is going in this, whoops, the DL is going in this direction. Okay, so the magnetic field up here is going to have to be, if you notice, we're looking at, let me bring this equation, copy it down. Copy it, and whoops, and drop it down here. Let's just look at it a little bit. Sorry, this is calculating the magnetic field. So basically what you'll see is, we've got this cross again for the direction of the magnetic field. So if dl is going that way, we've got just generally the direction sort of this way. B, the vector for B is going to be perpendicular to anything that has either one of those in it. So basically it's going to be coming out of the display and going into the display. So again, if you're going to look at it, so if I'm going to look at let's say this is the wire pointing at our face. So this is the wire with the current coming out. And A is going to be sticking out. Basically, the magnetic field at all points has to be perpendicular to it. So it's going to be basically going in a circle around. So this will be the magnetic field at every point. So let's do the calculation. Specifically, dB is going to be mu 0 I over 4 pi dx over x squared plus a squared sine of theta. And again, it's going to be very much like what we did for the infinite line with infinite electrical charge. So I'm not going to go into the details too closely, just sort of remembering what we're doing is, in this case, we're taking these small lengths and figuring out what the component is due to the magnetic field component to do any of these for something sitting here at the distance a, and then we're going to integrate over all the segments. And then we're going to basically replace sine of theta for sort of the distances involved. Again, I'm not going to go into the details. I think it's just very similar to what we did for the electrostatic case. So mu naught I over 4 pi dx over x squared plus a squared, a over square root of x squared plus a squared square root of. And then again, you kind of I won't go through it, but we do that sort of the tan substitution, if you guys remember those substitution, etc., the secants and stuff. We did that substitution to figure out the integral. That's long story short, the answer is going to be mu naught I over 2 pi a, which again is very much like the electrical case. Of course, in this case, instead of charge and epsilon naught, we have mu naught and current. Okay. All right. So let's see. And this kind of like gives us a view of why, sort of going back to our initial sort of this graph here. Okay, with the magnetic field pointing in these directions. Kind of gives us a view. If you guys remember, we started the whole discussion of the magnetic field by saying so this is sort of going back to day one of magnetism. Sorry. To day one of magnetism. We were talking about a wire that had a current, and then basically it's this case, right? And we said that if there is a charge with certain velocity, it would get a force on it. Okay. And basically we kind of get an idea now what's going on. We basically get a magnetic field that's, above, if the current's going in that direction, up here it's coming out of the board. So again, in a circular way, if I look at this across, the magnetic field is going to look like this around the wire. And the magnetic field is going to be going into the board over here. So going into the board, coming out of the board. And when this velocity takes off, basically the force on this charge is going to be the cross product of the velocity of this thing with the magnetic field. And of course, since the magnetic field here, for example, is going into the board, and this is going in this direction. So you can see kind of, let's see if I do the right-hand rule here. How does this look? So it'll be looking, so it basically looks like a force that's going in this direction. Okay, so it gives you an idea of why that's the case, basically. So that's what would be happening. All right. So now, so again, I'm hoping you guys see the analogies between magnetic and electrostatics and the magnetic field laws for a constant current. We ended up with this Biot-Savart law. And now we're going to talk about something that looks a lot like, just like we had Coulomb's law and we had something called Gauss's law that helped us, give us some really simple solutions under very specific cases. We have something like that for magnetism as well, and that's called Ampere's law. Okay, and what basically it says as far as Ampere's law, well, let me see. So basically, think about this. There's a current coming out of the board again, and then that we know gives us a magnetic field here. Let's think about this way, and then think about there's an angle phi here. Okay, so I is coming out of the board. Okay, so the B here is going to be mu naught I over 2 pi r. We had that. So A here instead of A, let's call this R. Okay, so this is just coming from our form our solution. Where was our solution? Here. So mu naught I over 2 pi A. Here instead of A, we're just going to keep this variable, call it R. And the magnetic field is circulating around the current. So let's say it's sort of going in the direction of this angular direction phi, okay, going around. So if you think of, what we were thinking in terms of a electric field. So again, remember we're trying to come up with something similar to Gauss's law. If you were thinking the analogy of having a charge and then, electric field coming out of the charge, we have like a very different situation because the E field lines are, emanating out of the charge, whereas in this case, the magnetic field isn't really emanating from anything. It's going in a circle, so it's closing in on itself. Okay, so it's not, it doesn't have the beginning, doesn't have an end. So if you think of the line integral, of a magnetic field, is just going to be, the line integral is just going to be zero. It's going to come back to where it started. Whereas in the, sort of electric field, there is no concept of circularity that things are coming back or anything. Okay, so let's think about this. So if you think about a surface integral here going around the circle, around the wire of B dot dr. Okay, so think of let's see if we blow up kind of blow this guy up, this thing. Let's say we blow this up over here. It's a little easier to look at. So we have, there's The magnetic field is doing that. And E sub phi is doing that, that's the tangent. Okay, that's a small amount of, oops, I keep saying theta, but it should be phi. We call the angle phi. So it's d phi, and then r is the radius. So we're just looking at this wedge and looking at, the magnetic field there. Okay, so if we're looking at, so in this case, so dr is going to look like r d phi e phi. Okay, so this guy is going to equal to mu naught I over 2 pi from 0 to 2 pi. We're going to do this dot dr, so it's going to be r d phi. Of course, r over, let's see what I have, over r. And this is just going to look like mu naught I. And that's really independent of radius of circle. So this is as if, like, you're looking at, if you're looking at the integral of b dot dr, sorry, around the whole circle. Okay, the result is just kind of depend. This doesn't matter on the radius of the circle or anything. It just depends on like what kind of current, how much current is going through it, going through this circle, right? So again, remember that the current's coming out of the screen here. Okay, and so this is like very analogous to much like Gauss's law, where we were looking at the electric flux equaled sort of a surface look like the charge of like equal to the total charges in the surface. We have sort of the same thing in terms of a magnetic, I guess, magnetic field times, we're going around this thing, the total magnetic field is, is equal to the currents going through it. And this also ends up being the case even if, much like Gauss's law, even if we had a kind of current coming out, let's say current was coming out again, coming out of display. So you'd get the same result if you had a weird shape around this thing. So again, imagine if we, because the idea is that each dr, let's see, where should I put a dr? Each dr would have a radial and a radial and the tangential part. So if you looked at any dr, so if I zoomed in on this, zoom in on it, you're going to end up with a dr, r d phi, and we do have the d phi. So let's do it this way. So a total dr is going to be, I guess this one have a vector. sorry, this would be dr without a vector e sub r. So dr would be dr e sub r plus r d phi e sub phi. So a angular component and a radial component. And then b is equal to mu naught I over 2 pi r e sub phi. And so b dot dr is equal to mu naught I. So again, I'm putting this as the case because the magnetic field is going to just have an angular component. Okay, so that's mu naught di over 2 pi r e sub, well, I'm not sure what that's down, so I guess. So I want to do the b dot dr. So what does that look like? Start from scratch. Mu naught I over 2 pi r e sub phi times r d phi e phi. Okay. The reason for this is because e sub phi and e sub r, so e sub phi and e sub r are by definition perpendicular to each other, meaning that if we take this and do a sort of a dot product with this guy, this component and this component, there's going to be nothing on this dot product because e sub r and e sub phi are perpendicular to each other. So all you would end up with is this component and this component. Okay. And so even in this weird case, you end up with b dot dr is mu naught I over 2 pi. So of course, this guy and this guy just gives you 1. This guy cancels out this guy, so you just end up with 2 phi d phi. Okay. And then if you integrate over the whole surface, you end up with mu naught I over 2 pi times 2 pi or mu naught I. Okay. So let's take in all that. Let me kind of summarize everything. So, just one last thing is that by superposition, we can say if for one guy that's the case, for multiple other guys, currents coming in and going out, you should be able to just sum their contribution, again, by superposition. Okay, so let me state that. So this is Ampere's law is, say if you have a bunch of currents, these are currents going in to this screen, currents coming out of the screen. So depending on what they are, so the b dot dr is equal to the sum of mu naught all the currents for J. Okay, so these are basically these I sub j's are any currents that penetrate the surface generated by the loop. What does that mean? It means basically this loop is defining the surface basically any currents that are coming and going this, the sum of all those currents multiplied by mu naught is equal to B dot dr around the loop. Okay. And the other part of the Ampere's law is, so this is the magnetic field essentially around this loop. Okay. And then if you want to think about the magnetic field, double integral of the magnetic field on the surface, any closed surface. Remember, this sign means any closed surface, double integral. So double integral means surface integral, and the circle means closed surface. That B dot dA is equal to 0. Because if you can think of, by the way, sorry, this is Ampere's law right here. Okay, so these are additional things I'm telling you. So remember Gauss's law had the electric field E dot dA, so it had E dot dA on a surface, and that equal to the charges inside. The sort of the magnetic version of that, or Ampere's law, is talking about going around any loop that's including currents inside, and that basically gives you the sum of the currents. But in the case of you're like integrating and on the surface, you'd always end up getting 0, because if you think about it, like let's say if it was any surface, I'll try to draw a surface to my best of my ability, you have no currents are gonna sort of stay there. If you have any currents, they're gonna go in one place and come out the other, sort of by the nature of currents, because the currents are going to have any starting location or ending location. Okay, so we would need any line that that comes in needs to leave. So basically, the sum total of all the what's coming and going here is going to be 0. Okay. In addition to that, we also have a similar thing for E dot dr around any closed loop. It's going to be 0. Okay, so this comes from E field being conservative. So this means if the electric, so this is we're restating stuff that we had from before. I'll tell you why I'm doing that. So if the E field goes to any point, comes back to the same place, is equal to 0. Okay, so we showed this in the electric field part. And then finally we have the Gauss's law, which is the closed surface integral of E dot dA, or the electric flux is going to be sum of the charges over epsilon naught. Okay. And so the total of all 4 of these are known as the integral form of Maxwell's equations. And we'll see, there's sort of like a differential form of Maxwell's equation. So anyway, this covers all the cases of electrostatic situations. And magnetostatics. So remember, electrostatics was when the charges are stationary, they aren't moving, and they have never been moving. So that's electrostatics. We did that again to get around relativistic issues and not to keep track of historical data on the charges. And so we got Coulomb's law, Gauss's law, and we played around with those. Magnetostatic means that the current that's generating the electromagnetic field is constant, it hasn't changed, it's steady, and so is the positional loop. So for those kind of cases, for those situations, basically these four equations cover, basically can give you all the information you need for all of those situations.